Hello and welcome to the mind map of reactions and balancing them for Year 9 Science in Australia. Alright, so we're going to start off first. If you want to take a picture of the whole mind map, do it now. And because we're going to zoom in. Now, Mr. Lavoisier from a long time ago said that matter cannot be created nor destroyed, only transformed. So that means the matter involved with the reactants must be the same as the matter in the products. So the first step in balancing an equation is to write the correct formula for the reactants and the products. Now, once the correct formula for each is done, the only way that we can balance is to change what we call the prefix in front of the reactant. So up here, we've got a 2 in front. So that's what they mean by the prefix. All right, and then what we have to do is just make sure that we can balance the same number of atoms on the reactants as the same number of atoms on the products. And when they do, we say that it's balanced. So there are a number of reactions we must know in Year 9 Science. The first one is an acid plus a metal. When it says active metal, it just means it must be reactive. It means it's not unreactive. Right, so it's an acid plus a metal gives us a salt plus hydrogen gas. Now, when it comes to the salt, we can tell what salt it's going to be depending upon the acid. So if the acid is a hydrogen chloride, then we know that the salt is going to be the metal from the active metal plus the anion from the acid, and then we also end up with hydrogen gas. Now, hydrogen gas can be tested for by using the POP test. The next one is acid plus a base, and then we normally use metal hydroxides as the base is going to give us a salt plus water. Now, once again, salt is going to be the metal from the metal hydroxide, and the anion here is going to be from the acid. And then water is just H2O. Okay, so here we have an example of nitric acid. So nitric acid is HNO3. So in the salt, we know it's going to be calcium from the hydroxide, and we know it's going to be the nitrate from the acid, and it gives us calcium nitrate plus water. All right, the third one is an acid plus a metal oxide, and again, this gives us a metal salt. So the metal comes from the metal oxide, the anion for the salt comes from the acid, and then gives us a metal salt plus water. Okay, so if we've got sulfuric acid and sodium oxide, then we know that the metal salt is going to be the sodium from the metal oxide, and it's going to be the anion from the sulfuric acid, which is sulfate, and then it also gives us water. Acid plus a metal carbonate is going to give us a metal salt plus carbon dioxide plus water. Now, the test we can do for carbon dioxide is to bubble this through lime water, and lime water should go cloudy, and if you leave it for long enough, it'll go back to being clear again. But that is the test for carbon dioxide. It's called the lime water test. Then as we scroll down is acid plus a metal hydrogen carbonate. Now, hydrogen carbonate is HCO3, so it's slightly different than the carbonate up here because there's an extra hydrogen involved. It still gives us the same products, being a metal salt plus carbon dioxide plus water. We can still do the lime water test to prove that it's carbon dioxide being produced. It's just a little harder to balance because of that extra hydrogen in the hydrogen carbonate. All right, then we get to combustion reactions. Now, a combustion reaction just means a substance is reacted with oxygen to produce heat. Okay, it normally occurs spontaneously at high temperatures, but if it doesn't, we can set fire to it, and that's a pretty good way to ignite a combustion reaction. But you can combust either non-metals, and sometimes you can combust metals as well. Okay, but anytime you set fire to something in the presence of oxygen, we call it combustion. Okay, then we've got combination reactions. Now, a combination reaction is where you get two smaller substances, react them together to form one larger substance. And here we've got three examples: barium plus fluoride, or fluorine gas gives us barium fluoride. Okay. Magnesium oxide plus carbon dioxide gives us magnesium carbonate. All right, so two smaller substances make one larger substance. Then we've got a decomposition reaction, which is the opposite reaction, which is a larger substance that decomposes it into two smaller products. And here we've got a good example, which is hydrogen peroxide decomposes into water and oxygen. And the test for oxygen is what we call the glowing splint. So we make the oxygen, we set fire to a splint, we let it go out, but it still has a red ember at the end. We then put it into the test tube where you have been collecting the oxygen, and it should reignite. Okay, if we go across to the other side, we start to look at what it means to be an acid or a base. So we have the pH scale, which runs from 1 to 14. 7 is neutral, and we can test this through what we call a universal indicator. So neutral gives us a color of green. Acids are 1 to 6, and an acid is a proton donor, and an alkali is a proton acceptor, and they are things from pH 8 to 14, okay? And that gives us the blues and purple using universal indicator. So acids are proton donors. They do taste sour. That's how you get the sour bears or the warheads that have a very sour taste, and that's just citric acid coated all over them. There are 4 major acids that I like to teach that are very commonly used, and they also allow us to tell the salt that's going to be produced in the equation. So hydrochloric acid is HCl, dissociates in water to hydrogen and chloride and makes a chloride salt. Nitric acid is HNO3, and it makes a nitrate salt. Sulfuric acid is H2SO4 and makes a sulfate salt. And phosphoric acid is H3PO4 and makes a phosphate salt. If we're looking at the comparison between acids and bases, here we have a lovely comparison table. We zoom in a bit more, and we can see that acids are sour, bases are bitter. Acids are watery, bases are slippery. This turns universal indicator red. This turns it bluey purple. Okay, so we'll zoom back out again, and then we'll go down to salts. Now, a salt is made up of a cation and an anion. The cation is a metal. The anion normally comes from the acid used. In the solid form, it forms an ionic lattice. It dissolves in water, and when it dissolves in water, it conducts electricity. And we've been through the 3 rules for balancing ionic formulae. Once you've decided you've got a cation first and an anion second, then you don't worry about the charges. We're just worrying about the numbers on the charges. And if the numbers are the same, then we do nothing. All right, we just stick them together. Like here we've got calcium, which is 2 plus, and sulfate, which is 2 minus, and we just smash them together and get CaSO4. If they're different, so for instance here we've got Al3 plus, that's aluminium ion 3 plus, and OH minus, then we need to swap and drop. The 3 goes to the bottom, and the 1 from the hydroxide goes back to the aluminium, so we really can't see it. We've just got Al because there's only 1 of them, and so it becomes Al and in brackets OH3, which means 1 aluminium and 3 hydroxides. All right, and then if we've got a cation that is +4 and an anion is -2, it just becomes cation anion 2. So here we've got lead 4 plus and oxygen 2 minus. Rather than have lead 2, oxygen 4, we just go to cation anion 2, so PbO2. All right, and then when it comes to energy in reactions, we just look at whether energy is released or energy is absorbed. If energy is released, it's called an exothermic reaction. So here's exothermic. The reactants have more energy than the products. The amount of energy needed to activate the equation or the reaction is called an activation energy. But this gives off energy because there is less energy in the products than there is in the reactants. An endothermic reaction absorbs energy. It still has an activation energy, but the test tube you're doing the reaction in will get cold because the products are absorbing the energy. Right? So the products have more energy than the reactants had in them, and they get that energy from the environment. Okay, and as I said before, the gas tests for carbon dioxide, you bubble it through lime water and it goes cloudy, and if you keep doing it, it becomes clear again. For oxygen, you put a glowing splint into the test tube where you've been storing the oxygen and it should reignite. And for hydrogen gas, you put a match into the test tube where you've been collecting the hydrogen gas and it should make a popping noise. Okay, so back out and there you can take another photo if you want to, and that's it for us. Bye-bye.